Hello and welcome. My name is Karpinski, and today my group and I will be giving a brief lecture on turbo machines, and specifically the Pelton wheel. To begin, what even is a turbo machine? Well, turbo machines can be broken down into two categories, pumps and turbines. In general, a pump will add energy to a fluid, while a turbine will take energy away from a fluid. Typical turbo machines include multiple blades attached to a rotor, with an inlet or an outlet. An example is pictured here. While the flows of fluid through a turbo machine may seem complicated at first, they actually can be simplified by the following equation. Here, U is the blade speed, which can be written as omega times the radial distance from the axis of the fan. W is the relative velocity. Picture this as the velocity seen by a person riding on the fan blade. Now V is the absolute fluid velocity, which is the vector sum of the relative velocity and the blade velocity. This equation is very important as the fluid velocity and blade speed can be used in multiple equations to calculate values like shaft torque and shaft work. For today, we will specifically explore the Pelton wheel, which is actually pictured right behind me, and dive into a few useful equations that are derived off the simple velocity equation I just explained. Now on to Craig, who will deliver an electric presentation on Pelton wheel basics. Craig, take it away.
Thank you, Zach, for that energetic introduction. Now, speaking of energy, the Pelton wheel is a special type of turbine where we can harvest the energy from the system by diverting the velocity of the fluid from the original direction out to the sides, as you can see in the picture on the right. This is why we call them impulse turbines. Now, in solving these problems, we found that there were some very useful equations which even related back to what we were learning in the beginning of the semester. The first of which being the Bernoulli equation, although this one includes loss because oftentimes in these problems we're dealing with flow from the top of a dam all the way down to the turbine, and we get significant losses in the pipe as the fluid flows. Additionally, we have the continuity equation, which can also apply to the pipe and the fluid as it flows downward. Now, if we make some simplifications to the Bernoulli equation simply off the parameters that we know for these dams, then we can get a simplified Bernoulli equation just for these turbines. Now, you can see that there's a loss term in this equation, and that loss term is defined by the friction factor, the length and diameter of the pipe, and also the velocity of the fluid flow. Now, our main concern is the shaft work that we can get from these turbines. And this shaft work is defined by rho Q, which is just the mass flow rate, U, which is the blade speed, and then both terms in the parentheses represent the tangential velocity component of the flow. The beta term is also the angle at which the flow exits. Now, lastly, U, which is the blade speed, that provides the maximum amount of power is V1 over 2. This results from the fact that we need both force and motion to provide power. Now, Marin will walk you through an example which uses Pelton wheels.
So for the next part of our video, I'm going to quickly run through a Pelton wheel example where we're going to ignore minor losses, but the head loss is important. And we've set the diameter of the nozzle to 0.239 feet, which gives us the max power generation. And our goal is to find the max power, which is the work shaft. So this is the work shaft equation, rho QU times U minus V1 times 1 minus cosine beta. And we know that the max power is going to occur at U is equal to V1 over 2. So this equation simplifies to the work shaft is equal to negative rho Q V1 squared over 4 times 1 minus cosine beta. We're going to call this equation 1. Next, V1 can be found from applying the energy equation between the surface where the velocity and pressure is 0 and the outlet where the pressure and the height is 0. This equation then simplifies to this equation, where head loss is the friction coefficient times L over D times V squared over 2G. So we can find V from the continuity equation and the ratios of the diameters of the pipe and the nozzle. Then we plug this expression into equation 2, and equation 2 becomes Z0 is equal to 1 plus the friction coefficient times L over D times the ratio of the diameters times V1 squared over 2G. This equation can then be rearranged for V1, and I got 18.577 feet per second. Now back to equation 1, we need to find Q, and Q is equal to the area times the velocity. After plugging that back in, this is our final work shaft equation. After plugging in all of the known variables, I found that the work shaft is equal to negative 3.25 times 10 to the 4th feet pound per second. I converted this to horsepower and I found that the final answer is negative 59 horsepower.
Pelton wheels have many real-world examples. and they have many different applications. Commonly, they're used to harvest hydroelectric power. They range in many sizes, going from small and a few inches in diameter, all the way to very large, multiple ton ones that are mounted on vertical oil pad bearings in order to operate. The smaller Pelton wheels are typically used for harvesting power from small streams with low flow rates. Some of these systems actually use plumbing for water delivery methods. And then the larger ones are very large, as I said. The biggest ones in operation right now are at the Grande Dixent Dam located in the Swiss Alps. This dam has multiple hydroelectric power plants in use, and the production of these plants ranges anywhere from 150 megawatts to 1200 megawatts. So a lot of power. And then these are the sources we use to complete our project.